Look at any landfill serving industrial sectors, and you will find millions of tons of rigid, unyielding waste. Heavy machinery can barely dent these composite materials, let alone recycle them. We rely on conventional thermosets for demanding applications because they do not compromise. They deliver the intense heat resistance and dimensional stability required for aerospace components, structural adhesives, and deep-sea encapsulants.
OnlyTRAININGS. Learn what works in the industry.
The secret to that stability is a permanent cross-linked chemical network. Once these materials cure, the molecular bonds lock into place. You cannot simply melt them down or reshape them later. This highlights the engineering gap we must close. Conventional thermosets give us high stability but zero material recovery. Thermoplastics offer high recovery but deform under mechanical loads. The glowing space in the middle is the solution we need. That gap is exactly where today's R&D formulators are stuck. Corporate sustainability mandates are forcing engineering teams to take highly durable structural materials and somehow make them recyclable at the end of their life cycle. Fulfilling that mandate means figuring out how to break the single most basic rule of thermoset chemistry without ruining the material's structural integrity. Vitrimers and other covalent adaptable networks are widely pitched as the solution to bridge that gap. The mechanism relies on introducing controlled dynamic bond exchange directly into the cross-linked network. Expose the material to a precise combination of temperature, pressure, or catalyst activity, and the network temporarily rearranges. In theory, this allows you to repair the surface or reprocess the material entirely. Step into an actual lab and the reality hits hard. If you dump a reversible bond into a proven formulation, you almost always destroy its baseline performance. The most severe side effect you introduce with an adaptable network is creep. This animated diagram shows how creep behaves in practice. A material engineered to remain structurally sound slowly deforms, stretches, and relaxes when subjected to a continuous physical load. Every formulation adjustment is a direct trade-off between achieving end-of-life adaptability and maintaining structural integrity during service. This quadrant chart maps the incredibly narrow window of success in Vitrimer formulation. The horizontal axis measures dynamic bond activity, and the vertical axis tracks material stability and glass transition temperature. Many teams aggressively increase catalyst activity to speed up exchange and make reprocessing easier. The formulation immediately lands in a failure state in the bottom right. When exchange is too fast, you compromise shelf life, invite severe creep, and lose thermal stability. Attempting to correct this, teams engineer a highly rigid network with slow dynamics to protect the TG, hitting the opposite extreme in the top left. The material maintains physical strength, but reprocessing now requires impractical amounts of heat or time, defeating the recycling mandate. Your actual target is this narrow performance corridor. Here, the material remains entirely rigid during service and yields only to intentional activation triggers. Even when you hit that zone, boosting dynamic functionality can still trigger sudden drops in moisture resistance or chemical durability. The objective is not building the most dynamic thermoset possible. It is to design a material that remains completely dependable until you intentionally activate it. Most formulators attempt to locate that target zone by relying strictly on academic research papers. Academia provides excellent blueprints for cutting-edge theoretical chemistry and ideal scenario performance. But theoretical literature rarely accounts for industrial additive antagonism, scale-up failures, or strict regulatory compliance frameworks. Relying on in-house trial and error to bridge that gap costs months of blown budgets, wasted materials, and testing loops yielding nothing commercially viable. This matrix evaluates a calculated alternative, the OnlyTRAININGS Reprocessable Thermosets course. We map time to market, cost risk, and real-world troubleshooting across common R&D strategies. The training column's primary advantage is actionable guidance from industry-embedded experts who have already navigated specific scale-up failures. Investing in specialized training takes a vague, high-risk R&D mandate and converts it directly into a realistic, engineered material specification. Theory only matters if you can actually execute it in a lab. Let's look closely at your current project status. This is the Vitrimer Readiness Checklist. These are the specific criteria required to safely move a dynamic formulation from a lab bench to commercial scale-up. First, you must define the exact temperature, pressure, and time boundaries of your intended reprocessing window. Second, you must prove you have a concrete, measurable strategy for mitigating network creep over the product's entire lifespan. Third, you must guarantee that your end-of-life recycling claims are based on actual, scalable material recovery, not theoretical possibility. Failing to check even a single one of these boxes guarantees that the prototype will dramatically fail under harsh, real-world commercial conditions. This training is not meant for academic students looking for high-level theory, or for teams operating without a strict end-of-life sustainability mandate. It is built specifically for epoxy, composite, polyurethane, and coatings formulators actively struggling to make demanding materials recyclable. Succeeding here requires abandoning formulation habits that treat curing as a permanent, irreversible end state. You have to rethink your network architectures entirely, using proven, industry-tested frameworks to control the chemistry. If you need to stop guessing and start building qualified materials, click the link in the description to enroll in the Advanced Materials requires maintaining performance during service, while having total control over what happens to the network after the cure.